Okay, let me start now with the lecture of today. As I told you, it's not exactly a lecture, it's more a seminar in accordance what I already told you, in accordance basically with the structure of this course. In order to introduce the PSO, particle swarm optimization method, I would like to very shortly uh, present in a project. We can see that it's a relatively old project. We started in 21, we concluded in 23. Here is just a report or a presentation in the middle of the project. Then the name of the project is OptiRope, optimization in robotics. Again, particle swarm optimization methods. We have many methods here in my group. We work a lot. We work a lot with PSO in different fields, in different projects, but also in different fields, biological fields, um, economical fields, technical fields in any case. Is a method for optimization. For optimization of what? Of control, for optimization of, but better to say in identification, as I told you at the beginning, is very often used in general in identification. And now I clarify what identification is. During this lecture of today and next week, we will have a better idea what identification is. Identification is in a field with many methods. PSO is one of them. Is one of them. But the students typically like PSO because I would like to say we can really figure out what this method does. Conceptually, extremely easy. For the programming aspects, is not so immediate. Therefore, I use a particular didactic structure to introduce the software too. Today, the idea is to introduce the idea and to show the first software. Identification, again, means optimization. Basically, technique which allow to identify parameters, or in general, identification models. A model is a representation of a system. A model is a representation of the system. Model for us means mathematical model. Models, plural if you want, for us means mathematical representations. And these mathematical representations are based on optimization methods, always. Or let me say almost always. I would like to say always in identification, because we try to find a compromise between different complex representations. And I think during these two lectures, we can understand better. And if I have time, I will present also different techniques. Originally, I thought at different techniques, but anyway, I think PSO is it worthwhile to do. It makes sense. Very shortly, look, we have the robots. So think about a robot. The idea in the project, is to find. Let me see if I have a better picture. Yeah, this is better. I mean, yes, it's quite general, in which we can see that we can integrate the software in cloud. We can really it's really apply the PSO in complex optimized control and or identification techniques. I will clarify in these two lectures what is the meaning of identification techniques. Identification techniques equal, I would like to say, optimization techniques. Equals is not so well used this word, but in any case, identification techniques are based on optimization methods. Yeah, we can see in the general, it's our project in Loifana, in Liebenskind. But let me show you more technically. The idea or the goal of the project is to find, please pay attention, to find an rotational speed, omega, in this sense, omega of t, can change over time. And then translational velocity, v, of the end effector in this milling process, in order, please pay attention, to minimize, in the sense, is in a control, the PSO is in a control problem. The PSO is applying the project as method to obtain an optimal control, in the sense that we want to have a surface after the milling phase with minimal roughness. We will see in the example that next week a little bit better how we can use in identification. At this moment, just to have an idea about the method, I will present this PSO in the context of control. I would like to control the end effector of this robot, which is working on a surface. The idea is to find a rotational velocity of the end effector, omega of t, and a translational velocity, v, such that I will realize a surface of the piece, which I have the working piece to be milled, in order to have the roughness of the surface minimal, a very flat surface. Just quickly. Few words about optimization problems. With this picture, really a few words. We can see that, for instance, if I want to find the minimum of the surface, just to figure out, and a surface which depends of two variables, x and y, or omega and v, as in our example. Let image that we have just one minimum. Let me figure out a ball. In the surface, of course, it seems to be quite clear that the ball, if you consider the gravitational force, please pay attention, will end up in the minimum. The reason is it seems more or less that we have just one minimum. We have to be careful because on this part of the picture, it seems to be that somewhere we have another minimum. But let me think that we have just one minimum. It seems to be that we have just one maximum. This means we have just one minimum and just one maximum. Depends on the structure of the surface. And we say that the optimization problem is, I have another chat. Let me see. A problem to see. I didn't share. Stupid. Please stop me if you don't see. Excuse me. Stop me also, because sometimes I am not able to see the chat. Yeah, understand. Yeah, it's a shame now. Please stop me directly. Say me directly, because I don't see the chat very often. Yeah. Yeah, now I already told you 50 minutes about the slides. Yeah, how I can say, we have to restart very quickly. This is the system. As I told you, if you consider the robot, we have here a robot which is used to mill or to work on the piece in order to realize in a very flat surface. The idea is to find omega, rotational velocity, and v, translational velocity, very often translation velocity, in order to obtain the surface of the roughness of the surface with the minimal roughness. The roughness minimum. Very quickly now. Yeah. Few words about the optimization problem. We say that in this case, if you consider just one minimum and one maximum, or just one minimum, if you want to look for minimum, as in our case, that the optimization problem is convex if you have just one minimum. Here it seems to be one, but please pay attention here on the right part. It could be that you have another minimum far away from the domain. This aspect is extremely important, because if the problem is not convex, or if the minimum is outside of our research domain, we have to inform somehow, we have to put some variation in the PSO method. Nevertheless, this picture is interesting because we can understand as the BAL, we will go inside the minimum somewhere, assuming that we have just one minimum. Huh? Everything converge, let me say, everything converge in this minimum. If you consider the gravitational force, now of course we will end up this in this point. This means this BAL, please pay attention. Look for the minimum. Please think about my expression. The BAL independently varies if you have just one minimum in the domain. We have X and Y, the domain, or omega and V in our specific problem. The BAL will end up in the minimum. Now, if you don't consider the gravitational force, but you consider an algorithm as an force, the search force, we will see in the program. I can, in the same way, think that the BAL will end up in the maximum if the criteria or the criterion of the algorithm is organized to look for the maximum. Very important that we have just one maximum. Now, we say that the optimization problem isn't a convex problem in terms of minimum if you have just one minimum. We say that is convex problem in terms of maximum if you have just one maximum. This is the, let me say, the definition of the convex problem. Of course, we can also define in terms of flex. In terms of flex, the reason is if you have, do you remember the flex, subtle point, subtle point. If you have just one subtle point, of course, in this sense, we can think that if you have just one subtle point, in this case, we have also an convex problem in terms of subtle point. Again, if you have just one. Subtle point is, let me say, is intersection, I don't know if you remember math, an intersection between the minimum and the maximum, no? But one minimum and one maximum. We will see in detail with software. Okay, look at this picture. Now, it's a little bit strange. So I would like to animate, I'm not so able to do here. Yeah, now we can see the movement, I hope. Not yet. It is zoom. I hope that you can see the movement of the BALs, or particles. We are not speaking about BALs, but I introduced the BAL. No, why it doesn't work? Now, you can see the movement of this, yeah? I try to explain these two pictures, and then very quickly I will introduce the math, a few concepts of the math, and then we will move, at I would like to say in 50 minutes on the software. Look at the first picture, the upper part. We see in the surface with valleys and hills. Many valley, many hills. In this case, if I want to find the minimum or the maximum, as you like, we cannot say that the problem which you have here is a convex problem. Why is not? It's not because we have many minima, it seems to be, and many maxima. This means in accordance with the definition, we are not in the presence of a convex problem. In this sense, make extremely sense to apply the PSO. The reason I will clarify today and next week in depth. I mean, let me come back here. If this is the problem, we have more effective methods to find the minimum or the maximum. We don't need PSO. Now, in order to understand this sentence, I have to introduce a little bit better. I have to try to introduce the PSO. But keep in mind, PSO, keep in mind, then we will justify. PSO is an effective method in case the optimization problem is not convex. I mean, we need more than one minimum we need. Of course, the convex problem is always suitable because we have the global minimum. If the problem is this one, of course, how we can find the global minimum or the global maximum? uh, no, God knows where he is. But let me concentrate on this picture. The first picture is clear. Omega on x, v on epsilon, the surface defined somehow how the roughness of the surface of the piece changes over omega and v. Please pay attention here, we have to distinguish. I use the word surface in order to indicate the surface of the working piece, but also the surface of the cost function. Could be better to use another example. I mean, the surface of the cost function is fixed, this is what we have. And we have to find the minimum of a function which is defined over x and y. For instance, asset and liability. Where is the once I define something related to the bank system, what is the maximum? No? The maximum profit, something like that. To balance liability, money which I have in the bank, and investment in assets. The combination of X and Y in order to have the maximum. This can be a possible interpretation of the upper part of the figure. The idea is to find a combination of my investment in terms of money in the bank, my investment in terms of asset, in order to have the maximal value of the cost function. What we see in the upper part of the picture is the cost function, which I want to maximize in case of profit in investments. Of course, in our case, we want to find omega, rotational velocity, and v, translational velocity, of the end effector of the robot in order to minimize. Please pay attention of these two, the word which are two meaning. The surface of the working piece, but of course we have here also a surface of the cost function, which is the roughness. I don't know if it's clear what I intend. But let me go ahead with the example with the MATLAB will be extremely clear. More next week than today, but I would like to nevertheless introduce a didactical software which is the same in the application, in a real project. Of course, we have many variations in PSO. About the variation, I don't know if I will tell you. Probably in Santi, I will tell you in any case, because here in Loifana, we work a lot with PSO. We generate different variations also, self-made. Self-made. I try to introduce also for a research problem for you. Look at the second picture in the lower part of the slide. The second picture of in this slide, the second is in the lower part, I intend, is basically a map of the first picture seen, which I can see from up. I mean, I don't know if you know the concept of level curves. Level curves. I mean, try to imagine the upper part, the picture in the upper part. Let me say, if I intersect the upper part, excuse me, the picture of the upper part with plane parallel to the X and Y, parallel to the domain, let me say, roughly speaking, with different value of the z-axis, the level, no? Exactly, the z-axis, the level, with different value of the level. And if I project the intersection between this hyperplane and the surfaces in the domain X and Y, I will obtain the picture in the lower part of the presentation. I mean, in this presentation, in this lower part of the presentation, we can see valley and, or better to say minimum and maximum, better to say, because I can parameterize this line, which we can see in the lower part of the picture, with the level. I try to switch on the lateral camera in order to understand better this picture. And so we can proceed. Why I don't see now? Second. I hope you can see this. 0 here, I don't know, minus uh, x lower bound of x lower bound without minus. X upper bound, we will see later. Here we have a epsilon lower bound, epsilon upper bound, x and y. Yeah? Now, look at this, for instance. They look like something like that. Here I can write, for instance, let me, in order to understand what I intend with these level curves. Probably you know better than me. If I write here 5 meter, it doesn't matter what, could be also money, dollars. It's a level. Here, right here, 10. It's clear that from here to here, we have something which is increasing. Here, basically, we have the maximum, probably in the middle here, or somewhere inside, with, I don't know, 15 or 20. And we have basically a hill uh, which is going up. And in the contrary, if I have, for instance, here, 5 and here 10, as level, in this case, we have a valley because it's going down from this position and this position. Of course, they are not circular. They are not circular because it depends. It depends on the structure of the cost function, which I want to minimize or maximize, which is here in the upper part, which is here in the upper part of um, of my slide. I hope that I share. Okay, now let me go ahead with some a little bit boring aspects. And then we will move in 5 minutes to MATLAB. Look at these two equations. These two equations, and we come back with MATLAB. With these two equations represent the basic structure of the PSO. Let me start with the second one. Let me start with the second one. It is easy to be explained, even though in the software, the first one is the equation which runs firstly, and then the second one. It seems to be complex, but it's not. This is the basic form, of course. We can generate many differences, many, let me say, variations. No? Look at the second equation. The second equation is characterized by, let me say, basically two symbols, x and v. And then we have a complex predix and index. Nevertheless, x represent, please pay attention now, the matrix of the position of the particles. This is, we have some comments in the middle. And then we have, as in a matrix, rows and columns. We have n rows and d columns. Basically, in a swarm is mathematically represented by a matrix which consists of n row and d columns. Again, now, meaning of n rows and meaning of d columns. Again, swarm means matrices. And in particular, in the rows, we have the particles which we want involve in the search. Do you remember at the beginning I presented in a bar, no? One particle. Uh, One particle doesn't make much sense, but can be done. Of course, if the problem is convex, with one particle we solve the solution. We solve the problem. Huh? We find the solution in any case. If it's not convex, yeah, we need more one particle to increase the probability to find the minimum or the maximum. I would like to say also quickly, but just the probability. No? Again, n is the number of particles which we want to involve. This means the row in our representation represent the number of balls or birds in some books. D, the columns, the number of columns, represent the parameters which we want to optimize or which we need to optimize in our problem. Meaning in our example, we have two columns because we want to find the optimal omega, rotational velocity, the optimal v, translation velocity, in order to minimize the cost function. We represent the roughness of the workpiece. With the example will be extremely clear. Now, again on the mathematical expression, we can see x ped xi comma j. Now it's clear. It's clear because I is the index of the row, as in each matrix representation. Y is the index of the column. J, in our case, can be 1 and 2. We have two columns because we want to find omega and v. How many rows, how many particles? We will see. Of course, if the problem is not convex, theoretically, we have to involve a large number of particles, and a larger number of particles. But of course, this is a price. This is a price because the calculation, we will see now a little bit with the software. What is the index? Xk plus 1 equals xk, or up to k, x up to k plus 1 equal x up to k matrix. This means x I comma j up to k plus 1 equal and so on. Plus v. The meaning of the second equation is how the swarm will move on the domain during the search. We can see the picture here on the left part. We can see the picture. That's this particle starting from, let me say, exploring at the beginning the whole domain and then try to converge in one point. I use the word exploring, no? To explore. In fact, in the PSO, we distinguish two parts of the search. Exploration part, or the phase, exploration phase, and exploitation phase. I will come back on this later. But exploration means we try to understand where could be the best minimum. The best minimum is the minimum of the minima, the global minimum. And then we will try to converge on this region. But of course, it could be that some particle will indicate different minimum. No? We can see also on this picture. I will come back on this topic here. Exploitation is exactly the last phase in which we try to converge. Let me now analyze the first equation, then I try to open the software. And next week we'll go in depth on this software and other more practical software and real software which we used in the project, even though I try to simplify it for didactical reasons. Look at the first equation. The first equation update the matrix V. V is also in a matrix. In the literature, we say that x is the position, as I told you, of the swirl, and v is the velocity. Of course, we speak about a meta-heuristic velocity, nevertheless, in a matrix, which update the position, the senses, and the velocity, of course. Dimensionally, it seems to be that I add here position and velocity, which is not so really allowed. But if you think that I sum up x up to k plus v up to k plus 1, you can think that v is multiplied by step, which we can think about each step is the time. No, in the algorithms, step is the time. It's not a physical time, second millisecond, but it's the time of the algorithm. How many steps I need to converge? And then, of course, we can also realize in a quantification. We can also calculate the time, which depends on the microcontroller, depends on many things, the technical things, but we can see as in the time, we can calculate the time in accordance with many aspects of the algorithms. This means if you consider the V multiply one step, makes sense to speak about position and velocity, just to figure out, even though it's a meta-heuristic expression. Now, equation 1 is how update basically the velocity. Equation 1 is how update the velocity. Equation 2, as I told you, is how update through the velocity the position. If you don't speak about position velocity, we have two matrices to be updated at each step. Look at the equation 1 now. I will come back on this again with the software. We have three elements in the basic form. But of course, in our group, we implemented different algorithm with variations of this structure here. Look at this. W, I will tell you about the W within weight of W multiply V. Basically, I weight the old, let me say, velocity of this world. We will see that W could be also adaptive. I implement it in the software in an adaptive form. And let me say, in particular, typically, V change over time. Over time means over steps, decreasing. Basically, starting from relative large W on one side. We will reduce progressively W because at the beginning we try to emphasize the exploration part. We look everywhere, and then this means we increase the let me say the region in which I search with weighting with large W, the old velocity. We try to move everywhere, just roughly speaking. I think if you look at the picture here on the right part of the slide, we can see, try to interpret this picture here. We have two variables to be optimized, x1 and x2, or omega and v. And we can see here basically three vectors. One vector is exactly W multiply V IT. Please consider that here we are considering just one particle. Just one particle that in one step is moving from this point here, this origin, to this point here on the right, let me say, extreme right. And of course, is at the beginning, if y is big, I will move in a large domain. If W is small, is large, I will move in large domain. If I reduce W, this means I will move in a small region, exploitation phase. Then we have two vectors we can see here. Let me go quickly in that because I would like to open a little bit also the file. We have two vectors, K1 multiply R1, and then this particular vector here inside, plus K2 multiply R2, and this particular vector inside the parentheses. Let me quickly explain these two elements, and then I will open the file, even though I will not be able to conclude today with the file, but next week, in any case, I will conclude with PSO because we don't need to introduce the course. No? But let me go ahead here. What about K1? K1 is a constant. For default, equal to, I clarify why equal to, but could be also, we did in our variation, could be also calculated additively, always in order to weight the exploitation phase. I don't want to increase now the feelings. Let me go ahead and then through the project, I will tell you a little bit about the variations. But anyway, typically we can work together because otherwise the lecture is very heavy. Anyway, keep in mind, can be K1 and K2, these two parameters, also additively determined. Typically, K1 equal K2 equal to, I clarify now. R1 and R2 are two random variables. Random means, in our case, uniform random. This means the distribution is uniform. I don't know if you remember. If you remember, uniform random uniform distribution is constant distribution. This between 0 and 1. This means the mean value is 0,5. Now we can understand why K1 and K2 equal 2, because we want to weight these two vectors. We can see in the right part the vector characterized by G best minus xit, and the vector characterized, by P best minus x1t, and the vector characterized by G best minus xit. We want to typically, in the standard form, weight with the same parameters. Therefore, the mean value is 0,5 and multiply by 2, and we have a weight factor, random weight factor 1 for P best minus, and the weight 1 again for G best minus X again. Let me see if I forgot to say something at this moment. I don't think so. Let me clarify now the meaning of P best and G best. P best minus X, G best minus X, paid X index, I already told you. Let me clarify this. Look, P best I comma J up to K minus X I minus J up to K, a little bit difficult, the notation, is this vector here. Why is center here? Because in this expression here, we have WY matrix is plus. This means I translate the vector. I know that you know better than me the calculation with vectors. Please pay attention. We are speaking about matrices, but of course, in this representation, in order to understand, we are represented everything in terms of vector. It's also correct because we have just one particle here. We consider think about one particle and two coordinates, x1 and x2. It's perfect represented in the sense with a vector. Two coordinates, x1 and x2, or the omega and the v, and one particle. The movement of one particle in order to understand the meaning. What is P best? In accordance to the notation, is the matrices, because we can see the index I and J. I will be more precise analyzing the software, probably next week. I will introduce nevertheless also now. but is the matrix of the position at step k of my particles. And in particular, I will update each time, each position, each time I will find something better. Now, something better is a little bit difficult now to clarify, but using the software, I will be more precise. Basically, you have the position of my particle each time, but each position at each step k is better than the position as before, better in the sense if you look for minimum is less. I will update. What is gbest? Gbest, we can see this in a vector because we have just an empedix, J. In particular, if you think about this, is the row, because we can see that I move just J, this means I move just the columns, is the row with the best P best. This means on this population, I can find what is the bird, what is the ball. Let me speak about the bird, which find at step K the best minimum for this. Could be also the maximum, could be also a flex. And here, for P best minus X is in a difference between matrices. Here, G best minus X is in a particular difference, but MATLAB understands, each software understands that I will do the difference between this row and all row of the position X, meaning GP best minus X, I will basically update the P best, I do the difference with the previous values. G best vector minus X, what I am doing here, I update the old position, the old swarm, in accordance with the best bird. Because this calculation here in software means that I do the difference between a row and each row of the matrix X. Because J is the same. With the software, I will be more precise. I have a 15 minutes. I will open MATLAB and I will start to show you the example. And next week, I hope to, eventually I will use just another part of the lecture after next week, but I hope to conclude. Otherwise, we can also dedicate half hour also after next week. Now, let me open MATLAB and let me repeat everything within a didactical example in order to, because clear from this explanation is extremely difficult to, let me close this, to understand how we can, but I don't know really, believe me, I don't like. So I'm not able to work with Zoom. Now I blocked every, oh no. It seems to be I cannot do it. 1 second. Let me look at the program. MATLAB, where is MATLAB? Okay, MATLAB, let me call, found it. Okay, let me open. 1 second. I introduce the software in the lecture of next time. We will see that with this two software, we can really already start At the end of next week, already start with a possible exercise, or let me say part of the project. Now I will repeat everything with also introducing other aspects, technical aspects, but we will analyze in these 50 minutes and next week the structure of the program on the light, uh, on this, let me say, method which I quickly explain. Okay, let me share now. I found just the version, an old version of MATLAB quickly, but does not matter for our case. We will see here wavelet. I will tell you in this course about wavelet at the end. Yeah. Okay, let me open the software which you can find my study. At this moment, we have just one software which is split in two parts, just didactically. Just didactically. Let me open now. No, 1 second. And next week I will present also another software, a little bit more structured, but it basically is the same, but it's in a real application in the project. In order to understand that using uh, already this software, yeah, we can work. Give me just a second. I think it makes sense in this course to speak about this because can be used as a tool for the rest. First example. Huh? Okay, you can see here on the left part which we have indicated the programs which we have in the folder characterized by the path here. We can see here the path. Mhm. Let me show you at the beginning output function. In the middle, as you know from MATLAB, if you don't know, I tell you now, we have the M file. The M file is the MATLAB file in which I indicate the function. Please pay attention. This is organized so for didactical reasons. For didactical reasons. Uh, I mean, you can realize just one file. No, you can realize just one file. But didactically, I think in using this, we can understand better, in my opinion. Is the function, you know that the function must be called from a main program, but of course we can realize just one file. This is not necessarily to split. The name of the function is output function. It's our cost function, which we want, for instance, minimize. It's a didactical example. It's a function of x. We will see what x is in a few seconds. The function which we want to minimize in our didactical example consists of two variables, x1 and x2. Do you remember? I told you omega and v, x1 and x2. In the language of MATLAB, it's a little bit strange. This language, we have x parenthesis 1 parenthesis, x parenthesis 2 parenthesis. We can see here. No? The function which we want to minimize didactically is the paraboloid. The minimum equals 100 for x1 equal 2 and x2 equal 3. We can see here. Of course, for such kind of problem, I don't need PSO because the problem is a convex problem. And in particular, if I know exactly deterministically the cost function to be optimized, we can see directly where the minimum is. Or assuming that it's more complex. But if the cost function is a convex function, I can use different methods. Nevertheless, I use PSO because I would like to emphasize some possible problems in PSO, but in general in optimization methods. Because it's also true that I can use other methods. But PSO nevertheless has some advantages, numerically advantages, but of course also numerically drawbacks. We will see together. Let me open, this means make nevertheless sense to speak about or to present this example. Let me open the main file. Why doesn't open? Okay, I found it now. Very interesting. Very interesting. If you read a little bit the preamble, uh, the software will rely is a part of a software which was realized by me when I worked in ABB for a project. And then we modified together with Benedict and Leonard uh, for didactic reason. Look at this, tick. Somewhere there is a talk, I don't know if I cancel. Sometimes it's useful to calculate because between tick and tock, the calculator put in MATLAB, calculate the time, the running time in second, millisecond. Of course, this depends of the microcontroller, depends also on this on the MATLAB release because in some software is more in some release we have a command which is more optimized than the other one. In any case, we want to use TikTok as a possible reference. We have to say release of MATLAB and not only the microcontroller. But of course, depends also how we optimize the commands between tin and toc. Typically, we don't do that. We put the number of calculation number, product and subtraction, multiplication, multiplication and sum, algebraic sum. Multiplication and also division. Anyway, calculation load. There is also a standard form uh, to analyze the calculation load. But TikTok, I don't know if I talk, probably I cancel, but I can put it. Between TikTok, the machine directly say how many second, millisecond we need to run the command between tin and toc. CLC, I think, just a technical to cancel the command in command Windows, I think, but it's not extremely relevant. Clear all, clear the variable in the workspace. The variable in the workspace is linked here. We can see at this moment we have some variable for default, for the wavelet toolbox, basically for us irrelevant for the lecture. We will see later what I intend. Close all, close the picture. Otherwise, I think the picture remains open. Format along I would like to visualize the number with all possible decimals. RNG default is exactly what I told you, basically a uniform generation of random variables. That should be so. Fmin plot is the definition of a vector with infinite length. Infinite means anti the overflow. No? Very important now here. 5 minutes and then we will conclude for today. No? Lower and upper bound. I already told you about the lower and upper bound. You remember in the picture. We defined with the lower and upper bound the dimension of the domain which we try to look for the minimum or the maximum or the flex. This means somehow I don't need, but it's suitable to have a limitation on the research field or domain. Because if I write minus infinite plus infinite, of course, we have some problems. I mean, you have to know there is literature in which we can demonstrate that the probability to find the best minimum depends of the density of the particles. It's intuitive. No? If I have to look for the minimum, if I have to look for an object which is in this room, and I search alone, of course, the probability to find, in particular to find in a reasonable time, is less if we have we do together, no, with two people, three people, and so on. We have the lower and upper bound for the first variable and the lower and upper bound for the second variable. We can see here x1 changes, in our opinion, we will look for a minimum between -10 and 3, and the variable x2 will look for the minimum between -9 and 10. Do you remember? X1 was 2, the minimum, x3 was 3. We can see from here. No? Of course, if I know a little bit where these are, more or less, can help because I can use less particle, for instance, because the concept of the density, or in any case, if I consider the stop criterion, we can find quickly. This a priori knowledge depends very often from easy considerations. I mean, if I'm looking for omega and v in our example, you know that the robots have the maximal omega and the maximal v, and we need even though suboptimal inside this omega and v, minimum and maximum. Because if the robot does not is not able to run 1,000 I don't know round per second, of course, doesn't make sense to put this as upper bound. We can see here m the number of variables, x1 and x2, omega and v, is the number of particle, 1,000. We will see next week how it changes the results. Also in this case, even though I told you this, you have just one minimum, how is it possible to change? I will tell you why. I will tell you that. Therefore, makes sense to show you this example. Also, mathematically, we have just one minimum. Look, W min, W max, W min, I told you with this weight, we can change from a maximum to a minimum. And C1 and C2 in this example is fixed, equal to. I will tell you, we applied almost always also C1 and C2 variable or adaptively variable in order to adapt also exploration and exploitation phase. We can check some intermediate at intermediate steps, or generally in this example we will work until the maximal iteration. Maxram loops means if I can work with one loop or the two loops parallelly. This I didn't apply in this example, but anyway, it is possible variation technically, more technically than conceptually. And here we have two definition of buffers, which I don't use because we will use just one loop. No? Okay, I would like to stop here. Next week I will repeat shortly this part here, and then we will see exactly the software. And I will present also a more interesting software based on this. The difference is really a few things. Nevertheless, the last sentence, why also in this case, using one particle or using 1,000 particle, we have some differences. The reason is, we will see next week also in detail. Let me consider an optimization problem in one dimension so we can graph easily. I don't know. Here's the minimum x, what we want to write, 2. Ideal is 2. If the surface is totally flat, if the surface is mathematical, the surface, here is the cost function, isn't a surface, nevertheless. The cost function is totally flat. But in the computer, we don't have something like that. We have something like that. This means ideally remain x2, but it could be that is not the minimum. It could be a little bit here. It could be somewhere. This means if I have a few particles, it could be that will remain something like this. I don't know. Instead of 2 is 1 comma something. And this minimum here is not exactly an ideal minimum, it is 2, or something more close to x2, no? 2 comma, I don't know what. I will come back on this. Nevertheless, also numerically, because of the representation of the cost function inside the microcontroller is discrete, makes sense to speak about the PSO. But of course, in this case, I don't want to apply the PSO if I know that the problem is convex. The reason is, it's a shame that PSO costs. We will see next week this calculation aspect. Okay, if I have a question, I can answer question of PSO. Next week, we complete or almost complete. It could be that I need to do some consideration after next week. But I insist on analysis on PSO, but based on the software. Next week, I don't need to introduce the course to clarify many aspects of the course. This means it could be that I will finish, but sometimes I receive question, or to sum up, after next week, it could be that 20 minutes or maximal half hour before starting with another topic. Again, this PSO can be a good tool for control. I will emphasize also how important the identification, also next week. Identification, not only in terms of control, as today I told you about the omega and V, but also in identification of parameters. Probably somebody of you attended the classes in complementaire in different courses by me, also in bachelor, in which I do remember I try to identify also parameters. We can do also with PSO, because identification, the method of identifications are methods optimization based. Basically, in the context of the identification, always we defined an optimization problem to find an optimal parameter which fits, with find a compromise between some aspects of the representation of the system. If I have questions, I can answer your questions. Otherwise, I try to stop the record phase. About the record, I will look how I can. But in any case, I can send you in any case, or I can share. But I hope to generate a platform in which you can download directly. I hope. Okay, I hope that it was not boring. If I have a question, I have time for you. Otherwise, next time, same place, we go ahead with this method, which allows to generate interesting project inside control, identification, wavelets, we will see. Okay, if no questions, we will see next week, same time, same place, in Zoom, again, just in Zoom. When I will be in Lüneburg, the lecture is hybrid. This means we can meet me, we are in Corazzuzza, I think, no? Yeah, in Corazzuzza. But also per Zoom, it's hybrid form, it's allowed. The material is in my study. I don't think so that we need this. Is nevertheless I record it. Okay, I stop